Welcome to week 3. Today we're tackling one of the most challenging problems in e-commerce, managing a shopping cart. You might think a cart is simple, just a list of items, right? Wrong. A shopping cart is one of the most dynamic, constantly changing pieces of data in any system. Users add items, remove items, change quantities, apply coupons, all in real time. By the end of today, you'll understand why arrays aren't enough, how linked lists solve this problem, and how to manage massive data sets with SQL pagination. Let's dive in. Let's quickly recap where we've been. Week 1, we laid the foundation, learned about data versus information, RAM versus disk, how Python lists work in memory, and basic SQL select queries. Week 2, we focused on finding things fast, compared linear search, which is ON, with binary search, which is O log n, learned SQL where filtering, and optimized performance. Now week 3, we're moving to a new challenge, dynamic data structures. We're going to learn why the simple arrays we've been using aren't good enough for highly dynamic data like shopping carts. And we'll build our first advanced data structure, the linked list. We'll also tackle database pagination to handle massive data sets efficiently. The shopping cart is the most dynamic component in any e-commerce system. Think about how you use Amazon or any online store. You're constantly changing your cart, adding items, removing items, changing quantities from 1 to 2, applying discount codes, then maybe removing half the items before checkout. This happens in real time, in RAM, and it must be lightning fast. Why is this hard? First, the cart size is completely unpredictable. Could be empty, could have 100 items. Second, there are frequent insertions and deletions. User adds item here, removes item there. Third, we must maintain order. Users expect items to stay in the order they added them. Fourth, memory efficiency is critical. We can't waste RAM because thousands of users have carts open simultaneously. The question is, can our trusty Python list handle this? Let's find out. Our current solution uses a Python list, which is actually an array in memory. Here's how it looks. We have a cart with 5 items: iPhone 15, AirPods, MacBook Pro, mouse, keyboard. In memory, these items sit in contiguous blocks, one after another at specific addresses. Let's analyze the performance. When user adds item to end with append, it's O1, very fast. We already know this from week 1. But what about other operations? If user wants to insert iPad between AirPods and MacBook Pro, that's insert 2, iPad. This is ON, slow. If user removes mouse from middle, that's remove mouse, also ON, slow. If user removes first item, pop 0, still ON, slow. We learned this in week 1, but now we're going to feel the pain in a real scenario. The key issue is those contiguous memory blocks. Let's visualize why this is a problem. Let's walk through a realistic user journey. Step 1, user starts with empty cart. Step 2, adds iPhone 15 with append fast O1. Step 3, adds AirPods with another append fast O1. So far so good. But step 4, user changes their mind. Actually, they want to see AirPods first in cart, at the top. Now we need insert 0, AirPods, to move it to position 0. This requires shifting, slow. Step 5, user decides they don't want iPhone anymore, removes it, that's remove iPhone 15, more shifting. Here's the reality. Real shopping carts have 10 to 20 items on average. Shopping sessions last 20 to 30 minutes. During that time, user performs 50 to 100 add, remove, and reorder operations. If each of these costs ON, your system will crawl. Users will notice lag, they'll get frustrated, they'll abandon the cart. This is a real business problem. We need a better solution. Let's visualize how an array sits in RAM. Think of it like numbered lockers in a gym, all in a perfect row. Each locker has an address in memory, 0hex 1000, 0hex 1008, and so on, and an index, 0, 1, 2, 3, 4. The items sit right next to each other, contiguous, adjacent. Why does Python do this? There are benefits. First, fast random access if you want cart 3. Python calculates the address, start address plus 3 times item size, and jumps there instantly, O1. Second, it's cache friendly. When CPU loads one item, it often loads nearby items too, which speeds up sequential access. But there's a big problem. rigid structure. The locker analogy makes this clear. Imagine you're at the gym, lockers numbered 1 to 100, all in a row. Your stuff is in locker 50. Someone new comes and wants locker 3, but locker 3 is already taken. Solution? Everyone from locker 3 to 100 has to move their stuff one locker down. Exhausting, right? That's exactly what happens in RAM with array insertions. Here's the critical question we're asking today. Can we do better than ON for insertions and deletions? What would better look like? First, fast add anywhere, whether beginning, middle, or end, ideally O1. Second, fast remove anywhere, same thing, O1. Third, maintain order users expect their cart to stay in the order they added items. Fourth, dynamic size cart can grow and shrink without pre-allocating huge memory. Now, what are we willing to sacrifice to get this? First, we'll give up fast random access, saying cart 3 to get the third item won't work anymore, or will be slow. Second, we'll give up contiguous memory. Our items won't sit in neat adjacent blocks. Third, we'll give up cache optimization. CPU won't be able to load chunks efficiently. Is this trade-off worth it? For a shopping cart, absolutely. Think about it. How often do you access the fifth item in my cart? Almost never. You look at the whole cart, or you search for specific item by name. Random access by index is useless here. So we trade something we don't use for something we desperately need. This is the art of computer science. Here's our mission for today, broken into 3 hours. Hour 1. Understand the problem. We'll visually see why arrays fail for highly dynamic data. Introduce the concept of linked lists and compare memory structures side by side. Hour 2. Build the solution. We'll actually code a linked list in Python from scratch, implement add and remove operations, and achieve O1 performance for insertions. Hour 3. Scale to production. We'll switch gears to the database side, learn how to handle massive product catalogs with SQL pagination using limit and offset, and understand how disk and RAM strategies connect. By 3 p.m. today, you'll have built a production-ready shopping cart system that can handle thousands of users simultaneously. This is real-world engineering. Let's get started. Let's dive deep into scenario 1, insertion in the middle. Here's our current state. Cart has 5 items: iPhone, AirPods, MacBook, mouse, keyboard, at indices 0, 1, 2, 3, 4. User action. I want to add iPad between AirPods and MacBook. In code, that's cart.insert2, iPad insert at index 2. Now, critical thinking time. Pause and ask yourself, what must happen in memory? Where does iPad need to go? It needs to go to index 2, which currently holds MacBook. So what happens to MacBook, and mouse, and keyboard? How many items must physically move in memory? Think about it. The answer is coming, but I want you to visualize this first. This is the moment where you really understand why arrays are problematic. Here's the shifting process, step by painful step. Step 1. Original state 5 items, indices 0 through 4. Step 2. Python must first shift keyboard from index 4 to index 5 to make room. That's one memory copy operation. Step 3. Shift mouse from index 3 to 4. That's 2 operations. Step 4. Shift MacBook from index 2 to 3. That's 3 operations. Step 5. Finally, insert iPad at the now empty index 2. Notice something? To insert one item, we had to move 3 items. The cost was 3 shift operations for a 5-item array. Now imagine a cart with 100 items. You insert at position 2. How many items must shift? 98 items. That's 98 memory copy operations for a single insertion. This is why it's O and the cost grows linearly with array size. In a real e-commerce system with millions of users all manipulating carts simultaneously, this is devastating for performance. Let's go even deeper. Memory address view. Before insertion, our items sit at specific memory addresses: 0x1000, 0x1008, 0x1010, and so on. Each address holds one item. After insertion, we need 6 slots instead of 5. What really happens at the hardware level? First, Python allocates new memory block at 0x1028 for the new slot. Second, it copies keyboard from address 0x1020 to 0x1028. That's a physical memory write. Third, copies mouse from 0x1018 to 0x1020, another write. Fourth, copies MacBook from 0x1010 to 0x1018, yet another write. Fifth, finally writes iPad to the now empty 0x1010. Total, 5 separate memory write operations for one user action. Each memory write costs CPU cycles, consumes power, and takes time. In the microseconds world of computers, this adds up fast. When you have thousands of users all doing this simultaneously, your server's CPU is spending most of its time just shuffling memory around instead of doing useful work. This is inefficient. Now scenario 2, deletion from middle. Current state, cart has 6 items: iPhone, AirPods, iPad, MacBook, mouse, keyboard. User action. Actually, I don't want the mouse anymore. In code, cart.remove mouse. Mouse is at index 4. Question for you, what must happen now? We delete the item at index 4, that's obvious. But then there's a gap, an empty slot at index 4. Do we leave it empty? That would mean indices 0, 1, 2, 3, then nothing at 4, then something at 5. That's a discontinuous array indices with gaps. But Python lists don't allow that. They must be continuous, contiguous. So what's the solution? We must shift everything back left to fill the gap. Let's see this process. Here's the shift back process for deletion. Step 1, original state, 6 items. Step 2, we mark mouse at index 4 for deletion. I'm showing it as XXX. Step 3, shift keyboard left from index 5 to 4 to fill the gap. That's one shift operation. Step 4, shrink the array, remove the last slot, which is now empty. Final state, 5 items, no gaps. The cost was one shift operation for a 6-item array. But notice the pattern: we deleted from index 4 and had to shift everything after index 4. That's n minus k minus 1 items, where n is array size and k is deletion index. If we deleted from index 0 the first item, we'd shift 6 minus 0 minus 1 equals 5 items. Worst case, on. If we deleted from the last index, we'd shift 0 items. Best case, o1. But on average, we're deleting from middle, so on average, on/2, which is still on in big O terms. Arrays are bad at deletions too. Let's put insertion and deletion side by side to see the pattern. Insertion in middle. Before we have A, B, C, D, we insert X at index 2. After we have A, B, X, C, D. How many shifts? Items C and D moved right, so 2 shifts. Cost O of n. Deletion from middle. Before we have A, B, C, D, E, we delete C at index 2. After we have A, B, D, E. How many shifts? Items D and E moved left, so 2 shifts. Cost on. The pattern is clear. Insertion means shift right from insertion point. Deletion means shift left from deletion point. Both are on on average. Here's the irony. The very operations a shopping cart needs most, which are add and remove, are the ones arrays do worst. It's like buying a sports car that's terrible at accelerating and braking, the 2 things you need most. We need a different data structure. Let's deliver the big O verdict on arrays. Access by index, O1, good. Append to end, O1, good. But insert at beginning, on, bad. Insert in middle, on, bad. Delete from middle, on, bad. Search by value, on, bad. The verdict is clear. Arrays are guilty of poor performance for dynamic data. They're great for static or append-only scenarios, but terrible for insertion-heavy, deletion-heavy scenarios like a shopping cart. The sentence? We must find an alternative data structure, and that alternative is what we're learning next, linked lists. But before we code it, we need to understand the concept. How do linked lists achieve O1 insertions and deletions? The answer is brilliant and counterintuitive. Let's see. Here's the revolutionary idea that changes everything. What if we abandon contiguous memory? What if we let items sit anywhere they want in RAM? Old way with arrays, items must sit next to each other. Item 1 at 0 hex 1000, item 2 at 0 hex 1008, item 3 at 0 hex 1010, all adjacent. New way with linked lists, items can sit anywhere. Item 1 at 0 hex 1000, item 3 at some random address 0 hex 5C20, item 2 at completely different address 0 hex 2B40, item 4 somewhere else at 0 hex 7F08. They're scattered across memory. But this raises an obvious question. If they're scattered randomly, how do we find them? How do we know the order? If I'm at item 1, how do I know where item 2 is? The brilliant answer. Each item carries a clue to the next item's location. It's like a treasure hunt. Each chest doesn't just contain treasure, it also contains a map to the next chest. Let's explore this metaphor. Let's use the treasure hunt metaphor to build intuition. In a traditional array, treasure chests are in a neat row. Chest 1, chest 2, chest 3, in order. Benefit? Easy to find chest 5, just count. Problem? Hard to insert a chest between 2 and 3. You must physically move chests 3, 4, 5, and all later chests to make room. In a linked list, treasure chests are scattered randomly across the island. How does this work? Each chest contains two things. First, the treasure itself, that's the data. Second, a map to the next chest, that's the example. You start at chest A, which we call the head. Chest A contains gold coins data and a map saying, next chest at coordinates 510, pointer. You go to 510, find chest B. Chest B contains diamonds data and map saying, next chest at 12.3, pointer. You go to 12.3, find chest C. Chest C contains ruby data and map saying, no more chests, that's null, the end. This is how linked lists work. Follow the pointers. Each chest in our treasure hunt is called a node. That's the official term. What's inside a node? Two things. First, data, the actual value we want to store, like iPhone 15. Second, next, a pointer, memory address, to the next node, like 0x2b40. In Python, we create a node as a class with two attributes. First attribute, self.data, stores the value. Second attribute, self.next, stores the pointer to next node. Initially none because we haven't connected it yet. Example, we create node1 equals node iPhone 15. Now node1.data equals iPhone 15 and node1.next equals none. This node exists in memory but isn't connected to anything yet. It's like a treasure chest with gold inside, but the map page is blank. Next, we'll see how to connect multiple nodes to form a linked list. Now let's connect nodes to form a list. Step 1. Create 3 separate nodes. Node 1 with iPhone 15, Node 2 with AirPods, Node 3 with MacBook Pro. At this point, they're disconnected, floating in memory. Step 2. Connect them by setting pointers. Node1.next equal to Node 2 means Node 1's next pointer now points to Node 2. Node 2.next equal to Node 3 means Node 2 points to Node 3. Node 3.next equal to none means Node 3 is the last node. Visual representation. 3 boxes connected by arrows. First box is Node 1 with data iPhone 15, and next arrow pointing to Node 2. Node 2 has data AirPods, and next pointing to Node 3. Node 3 has data MacBook Pro, and next equals none. We have 2 key terms. Head is the first node. The entry point without head, we can't access the list at all. Tail is the last node where next equals none. This is our linked list. How do we traverse a linked list? Visit each node. We can't use indices like list 0, list 1, list 2. Those don't exist. Instead, we must follow the pointers. Here's the algorithm. Start at head. Set current equals head. While current is not none, print current node's data. Then move to next by setting current equals current.next. Let's walk through step by step. Step 1. Current equals head, so current points to node 1 with iPhone 15. We print iPhone 15. Then we move. Current equals current.next, which points to node 2. Step 2. Current is now node 2 with AirPods. Print AirPods. Move again. Current equals current.next points to node 3. Step 3. Current is node 3 with MacBook Pro. Print MacBook Pro. Move again. Current equals current.next equals none. Step 4. Current is none. The while loop condition fails. We stop. We've visited every node by following the pointer chain. This is traversal. There are two main types of linked lists. First, singly linked list. Each node has data plus next pointer. You can only move forward, like a one-way street. Visual, boxes with arrows pointing right, from A to B to C to D to none. Use cases, simple lists where you only need forward traversal, stacks, queues. Second, doubly linked list. Each node has data plus next pointer and previous pointer. You can move both forward and backward like a two-way street. Visual, boxes with arrows pointing both directions, bidirectional. Each node connected to both neighbors. Use cases, browser history where you need back and forward buttons, undo, redo functionality. Music playlist where you can go to next or previous song. For shopping cart, which is better? Doubly is better. Why? Because in the UI, user might want to navigate backward, like remove current item requires knowing the previous item. For now, we'll learn singly to keep it simple, but remember doubly exists for when you need it. Let's see array versus linked list, side by side in memory. Array. Contiguous blocks, all adjacent. A at 1000, B at 1008, C at 1110, neat row. Access cart 2, jump directly to address 1110, 01 instant. Insert, must shift everything, on slow. Linked list, scattered nodes, anywhere in memory. A at 1000, B at some random address 5C20, C at another address 2B40. Connected by pointers. Access the third node, no indices exist. Must start at A and follow pointers to B to C, that's on slow. Insert, just change pointers, 01 instant. This is the fundamental trade-off. Array gives you fast access but slow insert delete. Linked list gives you slow access but fast insert delete. For a shopping cart where users constantly add remove items but rarely access the fifth item in cart, linked list wins. Here's a preview of the magic 01 insertion. Let's insert node X between A and B. Before, head points to A points to B points to C. Steps. First, create new node X that's 01. Just allocate memory for one node. Second, point X.next to B that's 01. Just write one pointer. Third, point A.next to X that's 01. Just update one pointer. After, head points to A points to X points to B points to C. The cost? Create node 01 plus change two pointers 01 equals total 01. Notice what didn't happen. We didn't shift any items. We didn't copy any memory. We just updated pointers. Nodes B and C didn't move at all. They stayed at their original memory addresses. Only the pointers changed. This is the magic of linked lists. We broke free from the tyranny of contiguous memory and gained the freedom to insert anywhere in 01 time. In hour 2, we'll code this ourselves. Why does this matter for shopping carts? Let's analyze real user behaviors. Add item to end, array 01, linked list 01, tie. Add item to beginning, array ON, linked list 01, linked list wins. Insert in middle, array ON, linked list 01, linked list wins. Remove from middle, array ON, linked list 01, linked list wins. View entire cart, both ON, tie. You must look at every item. Access fifth item directly, array 01, linked list ON array wins, but who cares? Users don't say, show me the fifth item in my cart, that's useless. Real user session simulation. 20-minute shopping session, user performs 50 operations, adding items, removing items, reordering. With array, 50 times ON equals very slow. User notices lag between clicks. With linked list, 50 times 01 equals fast, smooth experience. Business impact, faster means better user experience, means higher conversion rate, means more revenue. This is why companies like Amazon use linked lists for shopping carts. But linked lists aren't perfect. When should you not use them? First, random access patterns. If you frequently need get the 100th item, array is 01, just calculate address and jump. Linked list is ON, must traverse 100 nodes. Second, binary search. Binary search requires O1 access to middle element, divide list in half, access middle. You can't jump to middle of linked list without traversing, so you can't do binary search efficiently. Third, memory overhead. Array only stores data. Linked list stores data plus pointers, extra 4 to 8 bytes per node, depending on 32-bit or 64-bit system. For small data, this overhead is significant. Fourth, cache performance. Array has data contiguous. When CPU loads one item, it loads nearby items into cache, very fast. Linked list has data scattered randomly across memory. CPU must load from different memory locations. Many cache misses, slower. Rule of thumb. Use linked lists for insert-delete heavy operations where you don't need random access. Use arrays for access-heavy operations where you don't change structure much. Let's see the big picture. Where are we on our journey? Week 1, we learned static lists, which are arrays. Pro, fast access O1. Con, slow insert-delete ON. Week 2, we learned searching arrays. Linear search ON and binary search O log N. Week 3, that's today, we're learning dynamic lists, which are linked lists. Pro, fast insert-delete O1. Con, slow access ON. Next, week 4, we'll build stacks and queues on top of linked lists. Real-world applications like browser back button and printer queue. Week 5, we'll learn trees, which are advanced structures used in file systems and databases. See the pattern? We're building up complexity step by step, from simple to advanced. Each structure has trade-offs. Understanding when to use which structure is the mark of a good engineer. Today's focus is linked lists. Master them, and you'll have a powerful tool in your toolbox. Let's analyze Amazon's shopping cart real-world example. Observations. First, items appear in the order you added them. This suggests a linked structure, not a random hash table. Second, you can remove any item instantly by clicking X. This suggests O1 deletion. Third, you can change quantity instantly. Again, O1 update. Fourth, you can reorder items by dragging. This requires pointer manipulation. Fifth, page loads fast even with 100 items. Efficient data structure. Under the hood, Amazon likely uses something like this. Cart item class with product ID, quantity, next pointer, and prev pointer. It's doubly linked, with head pointer, tail pointer, and size counter. Why doubly linked? First, drag to reorder requires access to previous node. You need to update prev.next when moving items. Second, removing from middle requires updating both neighbors. Third, navigating cart forward and backward for UI. This is production-grade engineering, choosing the right data structure for the job. Let's summarize hour 1. What did we learn? First, the problem. Arrays use contiguous memory, sitting in neat rows. When you insert or delete, you must shift items to maintain contiguity. This shifting is ON performance, which is unacceptable for shopping carts where users do this constantly. Second, the solution. Linked lists abandon contiguous memory. Nodes can be scattered anywhere in RAM. Nodes are connected via pointers. Each node knows where the next node is. Third, the trade-off. We lost fast random access, can't do cart 5 anymore. That's ON now. We gained fast insert delete, just change pointers. O1. Is it worth it? For shopping carts, absolutely yes. We don't need random access, we need fast modifications. Fourth, key concepts. Node is data plus next pointer. Head is entry point to the list. Without it, we can't access anything. Traversal means following pointers until you hit none. Singly linked has one direction, doubly linked has two directions. Next hour, we stop talking and start coding. We'll implement this from scratch in Python. Let's code the node class. Conceptually, a node has two parts, data and next pointer. In Python, we create a class called node. The docstring explains a single node in the linked list. Each node stores data and a reference to the next node. The init method is the constructor it runs when we create a new node. It takes one parameter, data, which is the value we want to store. Inside the constructor, we set self.data equal to data. This stores the actual value, like iPhone 15. Then we set self.next equal to none. Initially, the node isn't connected to anything, so next is none. That's it, very simple. This node class is the foundation of our linked list. Every item in the cart will be a node object. Let's create some node objects. We create 3 separate nodes. Node 1 equal to node iPhone 15, node 2 equal to node AirPods, node 3 equal to node MacBook Pro. What's in memory? Node 1 has data iPhone 15 and next equals none. Node 2 has data AirPods and next equals none. Node 3 has data MacBook Pro and next equals none. Memory visualization. These nodes are scattered randomly in RAM. Node 1 might be at address 0x1000. Node 2 at completely different address 0x5c20. Node 3 at 0x2b40. They're not adjacent. Currently, we have 3 disconnected nodes floating in RAM like islands. They don't know about each other. Next, we'll connect them by setting the next pointers. Now let's connect these nodes. Step 1 was creating the nodes. We already did that. Step 2 is connecting them via pointers. First connection, node 1.next equal to node 2. This means node 1's next attribute now holds a reference to node 2 object. In memory, it's storing node 2's address. Second connection, node 2.next equals node 3. Now node 2's next points to node 3. Third, node 3.next is already none. That's the end of the list. Visual result, 3 boxes connected by arrows. Node 1 points to node 2, node 2 points to node 3, node 3 points to none. Now we have one connected linked list. If we start at node 1, we can reach node 2 by following node 1.next, then reach node 3 by following node 2.next. This is a linked list. We've created nodes and connected them manually, but that's not practical. We need a container class to manage the linked list. Why do we need this? First, to manage the head pointer. Without head, we can't access the list. Second, to track list size, knowing how many items without traversing. Third, to provide clean interface. Users shouldn't create nodes manually. They should call methods like add item. Fourth, to hide implementation details. Users don't need to know about nodes and pointers. Let's code the scheduler class. Docstring. A shopping cart implemented as singly linked list. Provides O1 insertion at beginning. The init constructor. None. Initially empty cart. No first node. Sets self.size equals 0. 0 items. When we create cart with head pointing to nothing and size 0, this is our starting point. The head pointer is absolutely critical. It's everything. With head, we can access the entire list. Head points to first node A. From A, we can reach B. From B, we can reach C. We have access to all 3 nodes. Without head, we're lost. If head equals none, even though nodes A, B, C still exist somewhere in memory, we can't reach them. There's no way to get to A without head. These nodes become garbage, unreachable memory, and Python's garbage collector will delete them. Golden rule, never lose the head pointer or you lose the entire list. Analogy, head is like the entrance to a cave system. The cave contains treasure that's your data. Without knowing where the entrance is, the treasure inside is lost forever, even though it still exists. Always protect your head pointer. Let's add a simple helper method isEmpty. This checks if the cart is empty. The logic is simple. Return self.head is none. If head is none, cart is empty, return true. If head points to a node, cart has items, return false. Usage example. We create new cart, call is empty, it returns true because head is none. Then we add item, we'll implement add item next. Call is empty again, now it returns false because head points to something. Why is this useful? First, check before removing items can't remove from empty cart. Second, check before displaying show message cart is empty instead of error. Third, clear error messages to users. Your cart is empty, start shopping. This is defensive programming, always check edge cases. Now let's implement display traversal in action. First, check if cart is empty using our helper method. If empty, print your cart is empty and return don't try to traverse nothing. If not empty, print header showing cart size. Then the traversal algorithm. Set current equals self.head to start at beginning. Initialize position equals 1 for numbering. While current is not none, print the position and current.data, move to next by setting current equals current.next, increment position. This loop continues until current becomes none, which means we've reached the end. Example output. We see cart with 3 items, numbered 1 to 3, showing iPhone 15, AirPods, MacBook Pro. This is classic linked list traversal. Follow the pointers until you hit none. Time complexity? ON, because we visit every node once. But that's fine for display. We must show all items anyway. Let's test what we have so far. First, create empty cart and display it. Output. Your cart is empty. Works. Second, manually create some nodes and connect them. This is temporary. We'll add proper methods soon. Set cart.head to new node with iPhone 15. Set cart.head.next to new node with AirPods. Set cart.head.next to new node with MacBook Pro. Set cart.size equals 3 manually. Now display cart. Output. Shopping cart with 3 items, numbered list showing all 3 products. It works. Our traversal is working correctly. But notice we're manually creating nodes and connecting them. That's ugly and error-prone. Users shouldn't have to think about nodes. Next, we'll implement add item method to hide this complexity and achieve O1 insertion. Let's implement add item. Strategy. We'll add new items to the front, the beginning of the list. Current state. Head points to iPhone, which points to AirPods, which points to MacBook. Goal. Add iPad to front, so head points to iPad, iPad points to iPhone, and the rest follows. Why add to front instead of end? First, we don't need to traverse to the end, which would be ON. Second, we don't need to find insertion point. Third, we just update head pointer. Fourth, this achieves O1. The trade-off is that newest items appear first in cart, reverse order from when they were added. Is this okay? Yes. In many UIs, most recent additions are actually more important. Users often want to see what they just added at the top. This is an acceptable trade-off for O1 performance. Let's see adding to front step by step. Step 1. Create new node with data iPad. In memory, we now have a new node with data iPad and next pointing to none. The existing list with iPhone, AirPods, MacBook is unchanged. Step 2. Point new nodes next to current head. The code. New node.next equal to self.head. Now iPad's next points to iPhone, the current head. Visual. Arrow from iPad pointing down to iPhone. Step 3. Update head to point to new node. The code. Self.head is equal to new node. Now head points to iPad instead of iPhone. Visual. Head arrow moves to iPad. Step 4. Increment size. The code. Self.size add 1. We went from 3 items to 4 items. Total operations. 4 simple operations. All O1 create node, assign pointer, increment integer. No loops, no traversal, no shifting. This is the magic of linked lists. Here's the complete implementation of add item. Docstring says add item to front of cart. Time complexity O1. Step 1. Create new node with the item data. Step 2. Point new nodes next to current head. This connects new node to existing list. Step 3. Update head to new node. New node is now the first node. Step 4. Increment size counter. Print confirmation message. Usage example. Create empty cart, add iPhone 15, add AirPods, add MacBook Pro, then display. Each add item call is O1, no matter how big the cart gets. Adding to front is always same speed. This is why linked lists are perfect for shopping carts. Let's test add underscore item. We create new cart, add 4 items one by one. Each addition prints confirmation message, added iPhone 15 to cart, added AirPods to cart, and so on. Then we display cart. Output shows cart with 4 items. But notice the order. iPad first, then MacBook Pro, then AirPods, then iPhone 15. This is reverse order from how we added them. Why? Because we add to the front. iPhone 15 was added first. It was at head. Then AirPods was added. It became new head, pushing iPhone behind. Then MacBook, then iPad. Latest addition is always at front. Total item shows 4. Our size counter works. This reverse order is expected behavior when adding to front. In many apps, this is actually desirable. Newest items appear first. Before we implement deletion, let's revisit traversal, because deletion requires finding the item first. Why does traversal matter? Before we can delete AirPods, we must find where AirPods is in the list. Here's a find item method. We start at head, set current equals self.head. While current isn't none, check if current.data equals target. If yes, return current, we found it. If no, move to next. Current equals current.next. Keep searching. If we exit loop without finding it, return none. Item doesn't exist in cart. Time complexity analysis. Best case O1 happens when item is at head, first check finds it. Worst case ON happens when item is at end, or doesn't exist, we must check every single node. Average case is ON/2, which simplifies to ON we expect to find item halfway through on average. So searching is ON. We can't avoid that in a linked list. But deletion itself can still be fast. Deleting from front is the easy case. It's O1. Scenario: remove first item from cart. Before, head points to iPad, which points to iPhone, which points to AirPods. Code: first check if cart is empty, can't remove from empty cart. Save self.head.data in removed item variable so we can return it. Then the magic. Self.head equal to self.head.next. This moves head pointer to the second node iPhone. The old first node iPad is now unreachable. It will be garbage collected by Python. Decrement size. Return the removed item. After. Head now points to iPhone, which points to AirPods. iPad is gone. Operations. Save data O1. Move pointer O of 1. Decrement integer O1. Total O1. No traversal needed because we're removing from front. This is fast. Deleting from middle is more challenging. Scenario: remove AirPods from middle of list. Before, head points to iPad, iPad points to iPhone, iPhone points to AirPods, AirPods points to MacBook. The problem: to remove AirPods, we can't just delete it, we must maintain the chain. We must change iPhone's next pointer to skip AirPods and point directly to MacBook. Algorithm: first, find the node before the target, that's iPhone. Second, change iPhone's next to skip AirPods. Third, point iPhone's next directly to AirPods next, which is MacBook. After, iPad points to iPhone, iPhone points to MacBook, MacBook points to none. AirPods is disconnected, no node points to it anymore. It becomes garbage, will be deleted by Python. Key insight: during traversal we need two pointers, current, the node we're examining, and previous, the node before current. This way we can update previous.next when we find the target. Here's the complete remove item implementation. Docstring. Remove item from cart. Time complexity, ON for search, O1 for removal. First, check if empty can't remove from empty cart. Special case. If head.data equals item, we're removing first node, just move head to head.next. Decrement size. Done. Return true. General case. We need to search. Initialize previous equal to none and current equal to self.head. While current isn't none, check if current.data equals target item. If yes, we found it. Remove by setting previous.next equal to current.next. This skips current node. Decrement size, print success, return true. If no match, move both pointers forward. Previous equal to current, current equal to current.next. Continue searching. If we exit loop without finding item, print not in cart, return false. This handles all cases correctly. Let's test remove item. We create cart, add 4 items. iPhone 15, AirPods, MacBook Pro, iPad. Display shows them in reverse order: iPad, MacBook Pro, AirPods, iPhone 15. First removal: cart.remove item AirPods. This removes from middle. Output: removed AirPods from cart. Display now shows 3 items: iPad, MacBook Pro, iPhone 15. AirPods is gone. Second removal: cart.remove item iPad. This removes from front, head. Output: removed iPad from cart. Display now shows 2 items: MacBook Pro, iPhone 15. Third test: try to remove iPhone 12, which doesn't exist. Output: iPhone 12 not in cart. Error handling works. Our remove item correctly handles all three cases: remove from front, remove from middle, and item not found. Production ready code. Let's summarize time complexity for all operations. Add to front. Linked list O1, array ON, linked list wins. Add to end. Linked list ON, unless we maintain tail pointer, array O1 array wins, but we don't add to end in shopping carts. Remove from front. Linked list O1, array ON, linked list wins. Remove from middle. Both ON, tie, both require search. Search by value. Both ON tie, both must check each item. Access by index. Linked list ON, array O1 array wins, but we don't use indices in carts. Display all. Both ON, tie, must show every item. Winner? For shopping cart use case, linked list wins. Why? Because add and remove are the most common operations users constantly modify their cart. Those operations are O1 with linked list, but ON with array. The operations where array wins, random access, add to end, are rarely used in shopping carts. We chose the right data structure. Look at what we built, a complete shopping cart system. Our head pointer to first node and size counter for number of items. We implemented 5 methods. Init initializes empty cart in O1 time. Is underscore item checks if empty in O1. Add underscore item adds T-front. This is our big achievement. Remove underscore item removes item in O1 time for search, but O1 for actual deletion. Display shows all items in O1. Our achievement: we built production-ready shopping cart with O1 insertions. No more slow array shifting. Memory usage is efficient. Each node uses about 32 bytes. Data pointer plus next pointer on 64-bit system. 100 items equals 3.2 kilobytes. 10,000 items equals 320 kilobytes. Very reasonable. This is real software engineering. Choosing the right data structure, implementing it correctly, achieving target performance. You should be proud. Hour 2 complete. What did we code? Node class as building block. To front. On search with O1 deletion, we built production-ready cart. Key learnings. Pointers enable scattered memory. We're not constrained to contiguous blocks. Head is critical. Losing it means losing entire list. O1 insertion beats on shifting. Massive performance win. Two-pointer technique, previous and current, enables middle deletion. Trade-offs. We lost random access by index, but gained speed in operations we actually need. Code stats. About 80 lines of clean Python. 5 well-designed methods. Handles all edge cases, including empty cart. Code is clear, readable, maintainable. Next hour, we switch gears to databases, learning how to handle millions of products with SQL pagination using limit and offset. See you after break. Hour 3, we're switching context now. Hour 1 was theory. Why arrays fail, how linked lists work. Hour 2 was building shopping cart in RAM using linked lists. Hour 3 is about handling millions of products on disk using databases. The challenge: Amazon has about 350 million products in their database. User searches laptop, maybe 50,000 results match. Question: can we load all 50,000 rows into RAM at once and send to user's browser? Absolutely not. That would crash the server and freeze the browser. The solution: pagination show results in pages, maybe 10 or 20 items at a time. Pages 1, 2, 3, etc. User clicks next to see more. Real world. Every website does this. Google search results, Amazon product listings, YouTube video feeds, Netflix movie browsing. Today we learn how to implement pagination with SQL. Let's see the danger of naive queries. Scenario: user searches laptop. You write select star from products where category is equal to laptop. If database has 50,000 laptops matching, what happens? Database reads 50,000 rows from disk, sends all 50,000 rows over network, returns maybe 100 megabytes of data. Your Python application receives 100 megabytes, tries to store it all in RAM, potentially crashes or slows down. User's browser receives massive JSON response, tries to render 50,000 product cards, browser freezes, page is unusable. Consequences: server memory overflow, You're using too much RAM. Network congestion. You're clogging the pipe with unnecessary data. User frustration. Page won't load. They leave your site. Wasted server costs. You're paying for bandwidth and CPU to transfer data nobody sees. This is terrible engineering. We need pagination. The pagination solution. Instead of loading all 50,000 results at once, load just 20 at a time. User experience. Page 1 shows items 1 through 20 with Next button. User clicks Next. Page 2 shows items 21 through 40 with Previous and Next buttons. Page 3 shows items 41 through 60, and so on up to page 2500 with items 49,981 through 50,000. Benefits. Fast page load. Loading 20 items is instant versus 50,000, which is slow. Less memory. 100 kilobytes versus 100 megabytes. Better UX. User sees immediate results instead of waiting. Lower server cost. You only transfer what's needed. Trade-off. User must click to see more pages, but that's totally acceptable. Psychology fact. Users rarely go past page 3 anyway. Most users find what they want in first 20 to 60 results. If they don't, they refine their search. So showing all 50,000 up front is wasteful. Pagination is the right solution. Let's learn SQL pagination syntax. First command, limit. The limit clause says give me only the first n results. Syntax. Select columns from table limit n. Example, get first 10 laptops. We select product name and price from products where category is laptop. Limit 10. What happens internally? Database finds all matching rows. 50,000 laptops match the where clause. If there's order by, it sorts them, then returns only first 10 rows. Crucially, it stops processing. It doesn't load all 50,000 into memory. Performance note. Database is smart. If there's no order by, many databases will actually stop after finding 10 matching rows. They won't even scan the whole table. This makes limit very efficient. Second command, offset. The offset clause says skip the first n results before starting. Syntax. Select columns from table, limit n offset skip. Notice they're used together. Limit and offset are a pair. Example, skip first 10 laptops, get next 10, that's items 11 through 20. We use limit 10, offset 10. Offset 10 means skip first 10. Limit 10 means return next 10. So we skip items 1 through 10, return items 11 through 20. Combined explanation. Limit controls how many rows to return. Offset controls how many rows to skip first. Together they give us precise control over which slice of results to retrieve. This is pagination. Here's the universal pagination formula. Memorize it because you'll use it everywhere. Offset equals page number minus 1 times 1. Uses offset 0. 1 minus 1 equals 0. 0 times 10 equals 0. Returns items 1 to 10. Page 2 uses offset 10. 2 minus 1 equals 1. 1 times 10 equals 10. Returns items 11 to 20. Page 3 uses offset 20. 3 minus 1 equals 2. 2 times 10 equals 20. Returns items 21 to 30. Page 4 uses offset 30. 4 minus 1 equals 3. 3 times 10 equals 30. Returns items 31 to 40. In Python code, define function getPage with page number and page size parameters. Calculate offset using the formula. Build SQL query with fstring, substituting page size and offset. Execute query and return results. This formula is standard across all frameworks: Django, Flask, Rails, Express.js. Memorize it. Critical lesson. Always use order by with pagination. Here's why. Problem without order by. Query 1 gets first 10 items with limit 10, offset 0. Let's say it returns A, B, C, D, E, F, G, H, I, J. Query 2, seconds later, gets next 10 with limit 10, offset 10. But wait, it returns F, L, M, N, O, P, Q, R, S, T. Notice F appears again. Item F was in page 1 and also page 2. That's a bug. Why does this happen? Because database order is undefined when there's no order by. Rows may return in any order, and the order might change between queries, maybe because other users are inserting data, or database is reorganizing internally. Solution. Always use order by. Example, order by product ID ensures consistent ordering. Now every query returns results in same deterministic order. Page 1 always has IDs 1 to 10. Page 2 always has IDs 11 to 20. Golden rule. Pagination without order by is broken pagination. Always include order by. Let's see a complete production-ready pagination query. We select product ID, product name, brand, price from products. Where clause filters to category laptop and price between 30,000 and 100,000, this narrows results. Order by clause sorts by price ascending, cheapest first, then by product name ascending as tiebreaker if two laptops have same price. Limit 20 returns only 20 results. Offset 40 skips first 40 results. What this does. Step 1, where filters to laptops in price range. Step 2, order by sorts them by price. Step 3, limit and offset give us slice 41 to 60. Result, page 3 of sorted filtered laptops. This is page 3 assuming product name 20. Page 1 would be offset 0, items 1 to 20. Page 2 would be offset 20, items 21 to 40. Page 3 is offset 40, items 41 to 60. This is real production code. Let's analyze pagination performance with real numbers. Scenario, 1 million products in database, user searches laptops, 50,000 match. Without pagination, you do select getting all 50,000 rows. Time, about 5 seconds, slow. Memory, about 100 megabytes, huge. Network, 100 megabytes transferred, expensive. With pagination on page 1, you do select with limit 20, offset 0, getting only 20 rows. Time, about 0.05 seconds, that's 100 times faster. Memory, about 50 kilobytes, that's 2,000 times less. Network, 50 kilobytes transferred, also 2,000 times less. Improvements, 100 times faster response time means happy users. 2,000 times less memory means you can handle more concurrent users with same server. 2,000 times less data transfer means lower cloud bills. Cost savings are real. On AWS, data transfer costs money. Sending 100 megabytes per request versus 50 kilobytes per request, huge difference when you have millions of users. Pagination isn't just better UX, it's better economics. Let's connect all the dots. How does everything we learned today fit together? The complete e-commerce flow. Step 1. Database on disk stores millions of products. We query with select using limit and offset, returns just 20 products. This is hour 3 content, pagination. Step 2. Application in RAM, Python, Flask, Django, receives those 20 products as JSON array. Might cache them temporarily in RAM using simple array for display. This is hour 1 content. Arrays are fine for small static data. User clicks add to cart on one product. Step 3. Shopping cart in RAM using linked list. This is hour 2 content. Stores that product ID using our O1 add item method. User modifies cart rapidly, adding, removing, changing quantities, all O1 operations. User clicks checkout. Step 4. Order is saved to orders table on disk for permanent storage. The circle. Data starts on disk, products, moves to RAM, cart, goes back to disk, orders. This is how real systems work. When should you use which data structure? Here's a decision framework. Ask, is data static or dynamic? If static, rarely changes, use array. Example, product catalog page where you're just displaying 20 products from database array is perfect, no insertions needed. If dynamic, frequently changes, ask, small or large data set? If small, under 1,000 items, use linked list. Example, shopping cart where user adds and removes items frequently, linked list gives O1 operations. If large, over 1,000 items, ask, in RAM or database? If in RAM, use linked list, possibly with internal pagination or chunking. If in database, use SQL with limit offset. Example, product search results with millions of rows. Database pagination is only option. Rules of thumb. Display only means array. Frequent insert delete means linked list. Millions of rows means database with pagination. Need random access means array. Need O1 insert means linked list. Make informed decisions. Week 3 complete. Let's summarize all 3 hours. Hour 1, understanding the problem. We learned arrays use contiguous memory, which requires ON shifting for insertions and deletions. Linked lists scatter nodes randomly in memory. Pointers connect those scattered nodes. The trade-off. We lost random access capability, but gained O1 insertion speed. Hour 2, building the solution. We coded node class in Python to represent each node. Coded chicad item method, our big achievement. Implemented ON search combined with O1 deletion. Tested everything with real card operations. Hour 3, scaling to production. We learned SQL limit for getting top-end results. Learned SQL offset for skipping rows. Mastered the pagination formula. Learned to always use order by with pagination for consistency. Connected our RAM strategies, linked lists, with disk strategies, SQL pagination. Achievement unlocked. Full stack data structure understanding. You now understand how data flows from database to application to user and back. This is real engineering. These aren't just academic exercises. These are real-world, industry-standard techniques. Linked lists in production. E-commerce sites like Amazon and eBay use linked lists for shopping carts. Music players like Spotify use them for playlist management. You can add, remove, reorder songs quickly. Browsers like Chrome and Firefox use linked lists for back-forward navigation. Each page visit is a node. Text editors like VS Code use them for undo-redo. Each edit is a node. Games use them for animation frames and particle systems. Pagination in production. Google shows 10 search results per page using limit offset. Amazon shows 24 products per page. YouTube feeds show 20 videos per page. Instagram uses infinite scroll, which is pagination under the hood. Gmail shows 50 emails per page. You've learned industry standard techniques that power the websites and apps you use every day.